Welcome, friends. Let's read through this article. I found this on Popular Mechanics. Objective reality may not exist at all, quantum physicists say. Reality might be in the eye of the observer, according to new research. So this is by somebody, Stav Dimitropoulos. Nice little graphic here. Okay, let's see the summary. One of the biggest mysteries in quantum mechanics is whether physical reality exists independent of the observer. New research from Brazil provides strong evidence that there might be mutually exclusive yet complementary physical realities in the quantum realm. Future research and the great quantum debate might give us super disruptive quantum technologies and probably startling answers to the world's greatest mysteries. Does reality really exist, or does it take shape when an observer measures it? Akin to the age-old conundrum of whether a tree makes a sound if it falls in a forest with no one around to hear it, the above question remains one of the most tantalizing in the field of quantum mechanics, the branch of science dealing with the behavior of subatomic particles on the microscopic level. In that field where intriguing, almost mysterious phenomena like quantum superposition prevail, a situation when one particle can be in two or even all possible places at the same time, some experts say reality outside of your own awareness, and there's nothing you can do to change it. Others insist quantum reality might be some form of Play-Doh you mold into different shapes with your own actions. Now scientists from the Federal University of ABC, funny name ABC, in the Sao Paulo metropolitan area in Brazil are adding fuel to the suggestion that the reality might be in the eye of the observer. In the new research published in the journal Communications Physics in April, scientists in Brazil attempted to verify the complementarity principle the famous Danish physicist Niels Bohr proposed in 1928. It states that objects come with certain pairs of complementary properties which are impossible to observe or measure at the same time, like energy and duration, or position and momentum. For example, no matter how you set up an experiment involving a pair of electrons, there is no way you can study the position of both quantities at the same time. The test will illustrate the position of the first electron, but obscure the position of the second particle, the complementary particle, at the same time. God does not play dice. To understand how this complementarity principle relates to objective reality, we need to dive back into history. About a century ago, a legendary debate took place in Brussels in 1927 between Bohr and the celebrated German Bohr theoretical physicist Albert Einstein during the Fifth Solvay Conference, the most important annual international conference in physics and chemistry. Here's a picture. That's Einstein with a mustache, and Bohr's right there next to him. So before the eyes of 77 other brilliant scientists who had all gathered in the Austrian capital to discuss the nascent field of quantum theory, Einstein insisted that quantum states had their own reality independent of how scientists acted upon them. Bohr, meanwhile, defended the idea that quantum systems can only have their own reality defined after the scientists have set up the experimental design. God does not play dice, Einstein said. A system behaves as a wave or a particle depending on context, but you cannot predict which it will be, argued Bohr, pointing to the concept of wave-particle duality, which says that matter may appear as a wave in one moment and appear as a particle in another moment, an idea that French physicist Louis de Broglie first put forth in 1924. Now there's some debate about how you pronounce this guy's last name here. The Complementarity Principle. It didn't take long after the conclusion of the 27th Solvay Conference for Bohr to publicly articulate his Complementarity Principle. Over the next few decades, the controversial Bohr notion would be tested and retested to the bone. One of those that experimented with the complementarity principle was American theoretical physicist John Archibald Wheeler. Wheeler attempted to reimagine Thomas Young's 18-1 double-slit experiment into the properties of light in 1977. The two-slit experiment involves shining a light on a wall with two parallel slits. As the light passes through each slit, on the far side of the divider it diffracts and overlaps with the light from the other slit, interfering with one another. That means no more straight lines. The graph pattern that emerges at the end of the experiment is an interference pattern, which means that the light is moving in waves. Essentially, light has both a particle and a wave nature, and these two are inseparable. Wheeler had his device switch between a wave measuring apparatus and a particle measuring apparatus after the light had already traveled through most of the machine. In other words, he made a delayed choice between whether the light had already propagated as a wave or a particle, and found that even after delaying the choice, the principle of complementarity was not violated. However, more recent surveys which attempted to apply the quantum superposition principle on a delayed choice experiment saw the two possibilities coexist, just as two waves on the surface of a lake can overlap. This suggested a hybrid wave-like and particle-like behavior within the same apparatus, contradicting the complementarity principle. Quantum-controlled reality. The Brazilian scientists decided to also design a quantum-controlled reality experiment. We use nuclear magnetic resonance techniques similar to those used in medical imaging. Roberto M. Serra, quantum information science and technology researcher at UFABC, who led the experiment, tells Popular Mechanics. Particles like protons, neutrons, and electrons all have a nuclear spin, which is a magnetic property analogous to the orientation of a needle in a compass. We manipulated these nuclear spins for different atoms in the molecule, employing a type of electromagnetic radiation. In this setup, we created an interference device for a proton nuclear spin to investigate its wave and particle reality in the quantum realm, Serra explains. This new arrangement produced exactly the same statistics as previous quantum delayed choice experiments. Pedro Ruas Dieguez, now a postdoctoral research fellow at the International Center for Theory of Quantum Technologies in Poland, was part of the study, tells Popular Mechanics. However, in the new configuration, we're able to connect the result of the experiment with the way waves and particles behave in a way that verifies Bohr's complementarity principle. The main takeaway from the April 22 study is that physical reality in the quantum world is made of mutually exclusive entities that, nonetheless, do not contradict but complete each other. This is a fascinating result, experts say. The Brazilian researchers have devised a mathematical framework and corresponding experimental configuration that allows the testing of quantum theory, particularly understanding the nature of complementarity, by studying the physical realism of the system. Stephen Haller, an associate professor of physics at Fordham University, tells Popular Mechanics. It is a study that highlights the long-standing adage of the iconic American quantum physicist and Nobel laureate Richard Feynman. If you think you understand quantum mechanics, you don't understand quantum mechanics, says Haller. There's much to learn about the theory, and research continues to make strides to understand even the basic principles, which is especially important as we move into the age where quantum devices and computing are starting to proliferate. Dieguez is elated. The fact that a material particle may behave like a wave and light like a particle, depending on the context, is still one of the most intriguing and beautiful mysteries of quantum physics, he says. Paradoxically, this inherent weirdness of quantum mechanics can prove quite serviceable. The more we unravel quantum mechanics, the more we are able to provide the disruptive quantum technologies outshining their classical counterparts. Quantum computers, quantum cryptography, quantum sensors, quantum thermal devices included, says Serra. Their reality might be in the eye of the observer as a very peculiar aspect of the physical reality in the quantum domain, and the mystery itself shows no sign of abating, both researchers agree. And that is it. Leave a like.